the goal of the project is to do video representation learning in a self-supervised way. And if you look at the literature, what you will see is that most methods are based on the VideoME pipeline, which is a mask and predict pipeline. And so if you look at the previous method, what you will see is that they will try to inject motion, but in an implicit way. By doing so, they change what they reconstruct or how they mask. Here in our case, what we do is that we try to inject motion, but in an explicit way. This is one of the main contributions, and the other contribution is also to change from reconstructing pixels to reconstructing clip features. Because what you would expect is that clip features are going to be spatially more semantically richer than the pixel ones. So if you look at the upper part of the pipeline, what we'll have is that using the input frames, you will feed them to a point tracker, off-the-shelf point tracker, to extract trajectories. We need to do it in a sparse way because extracting trajectories is kind of expensive. And so based on these extracted trajectories, you do exactly the same pipeline as VideoME. You encode visible tokens, you have a latent representation, you do the decoding of the spatial part, either by doing pixel reconstruction or clip reconstruction. And for the upper part, what you will do is try to reconstruct the masked trajectories, which means that at the end of the pre-training, we hope that this encoder is going to have motion information encoded. So if you look at the result that we have, for full fine-tuning setup on something V2 and KF400, we are state-of-the-art for both VIT base, and if we scale the model to a VIT large, we also beat the VideoME baseline by good numbers. What's really interesting to look at is that for linear probing setup, if you look at the VideoME baseline for motion-centric benchmarks such as something V2 or GIM, we have really a big gain of performance, because for those two benchmarks, understanding motion is really needed, which is not the case for spatial-centric ones, where you could expect to have good classification performance with only one frame, right? So that's the whole idea. Now, if you look at what I think one of the most interesting results that we have is that, what if we don't do this spatial reconstruction? What if we only do trajectory reconstruction? Then what you will have is that you would have better results than what if you did pixel reconstruction, which is actually VideoME. So this was really a really cool results. Cherry on the cake is, because we have access to motion information, what we can do is to improve the random tube masking that we have with VideoME, where we would have a uniform sampling strategy. Here in our case, what we can do is to, based on the motion information that we have, we can create a sampling distribution based on high motion and low motion tokens. Those would be the low motion tokens and those would be the high motion tokens, right? Based on those two bins, what we can do is to select visible tokens from high motion bins and low motion bins, so that we will make sure that the visible tokens that you have are either coming from the motion part and from the background part, which is a smarter way to do masking, and it comes at no cost, obviously, because those information are already present in the tracking trajectories. Again, for the different ablation that we do, having a denser grid leads to better performance, but this comes at a computational cost. So instead of increasing this grid for the code tracker, what we can do is to increase artificially, but doing some spatial sampling, which leads to the best performance in our case. Overall, the results are available on GitHub, and we also uploaded the pre-trained models and fine-tuned models on a Hugging Face so that you can use them directly for your own application.